So do you want to start recording again, Peter? Thank you. Let's see. Josiah, you ready?
Yep.
Okay, so welcome back, everyone. So our second speaker today is Josiah Jacobsen-Grocott from the University of Wisconsin, Madison. We'll be talking about characterization of strongly eta-representable of many 1 degrees. Thanks.
Okay, thank you. All right, so the definition of an eta representation first. So recall that eta is the order type of the rationals. So for a set A, the linear order L is said to be an eta representation of A if there is a surjective function f from omega to A such that L has the following order type of eta plus f of n summed over all n. And so basically each f of n is going to be a block of size n, and then between these blocks we're going to have this dense eta part that distinguishes how we tell them apart. All right, so we say that L is a strong eta representation if the function f is strictly increasing, and L is an increasing eta representation if f is just non-decreasing. And so we also say a set A has a computable, if a set A has a computable eta representation, then we say that A is eta representable. Similarly, if it has a computable strong eta representation, then we say it's strongly eta representable. Or if it has a computable increasing eta representation, then it's increasingly eta representable. So now we'll look at some operations on linear orders, some relations that are quite useful. So the successor relation on linear order L is defined to be that x and y is a successivity if x is less than y and the interval between them is empty. And the block relation is given similarly that we say that x and y are part of the same block if the interval in either direction is finite. So there's only finitely many points between them. And then a block of size n is a collection, or an ordered sequence of successivities at x0 up to xn minus 1, such that anything that's part of the same block as x0 is equal to one of these xi's. All right, and so it can be seen that the successor relation is always pi 0, 1 in the linear order, and the block relation is always sigma 0, 2 in the linear order. And if we look at the collection of blocks, so Feiner in his thesis showed that for a linear order L, the set of n such that L has a block of size n is always sigma 0, 3 in the linear order. So if we look at eta representations, for an eta representation L of a set A, we have that A is equal to the set of n such that n is a block of, such that L is a block of size n, which then gives us the following corollary that if A is a computable eta representation, then A is sigma 0, 3. And then if we look at strong eta representations, then Fellner in this thesis sort of gave us a different upper bound, so that if a set A has a computable strong eta representation, then A is in fact delta 0, 3. Fellner was also able to prove, going from the other direction, that every sigma 0, 2 and pi 0, 2 set has a strong eta representation. And so he made the sort of following conjecture that every delta 0, 3 set had a strong eta representation. However, Lerman was able to show that this is not true. There was a delta 0, 3 set with no computable eta representation. So not even a strong one, just no computable one. However, going in the opposite direction, then we were able to find a subclass of sets of eta representations, which is quite nice. So if A is sigma 0, 3, then A join omega has a computable eta representation. So not every sigma 0, 3 set has an eta representation, but if we look at the m degrees, every sigma 03 m degree has a computable Ada representation. However, in the strong Ada representations, it's not so nice. So Harris was able to show that Feldman's conjecture doesn't hold even for Turing degrees. He was able to show there is a delta 03 degree which does not compute any non-computable set with a computable strong Ada representation. So this left the following questions. So what are the strongly Ada representable sets? And what are the degrees with computable strong Ada representations? So Harris did answer some of these, and he used the notion of limitwise monotonic functions. So these are useful for some of stuff that I'll go over later on in this talk. So I'll introduce the notation now. So a function f from omega is limitwise monotonic if there is a computable function little f from omega squared to omega such that big F of n is equal to the limit in S of little f of ns. So that's the limitwise part, and it's monotonic in S, that is for every n in S, f of n in S is less than or equal to f of ns plus 1. So the idea is that we can computably approximate the values of f from below. So by the limit lemma, if f is limitwise monotonic, then f is delta 02, and hence if a is the range of f, then a is sigma 02. And so relativizing this sort of idea, you can see it's of the right form, and Harris was able to show that set A is Ada representable if and only if it is the range of a 0' limitwise monotonic function. So if we look at the proof of this in the direction of constructing the Ada representation, this is done uniformly. So Harris constructs these linear orders Ln, which have the form Ada plus f of n. And then he takes the sum over n of these ln's. And so from this, it can be seen that if A is the range of a strictly increasing 0' limitwise monotonic function, then A is the range of A is strongly Ada representable. However, Harris showed that this is not a characterization of the strongly Ada representable sets. So we now have a sort of bound from below of what they could be, but it's still unknown what they are, and it's not a characterization. So moving on to increasing Ada representations, Katch and Turetsky modified the notion of limitwise monotonic as followed. So a function f from the rationals to omega is support increasing limitwise monotonic on Q if there is a computable small f from the rationals cross omega to omega such that the following hold. So first we have the same limit notion. Big F of Q is equal to the limit in S of little f of Q and S. Then we want it to be monotonic. So for all Q and S, f of Q S is less than or equal to f of Q S plus 1. And then this is the support part. So there's the set S for the support, which is the collection of all rationals such that f of Q is not equal to 0. And we want that this support is order type omega, and that if we restrict f to its support, then it should be a strictly increasing function. So the intuition of how these are used is that the members of S will represent blocks of an increasing Ada representation. So when we discover some new block, when we're looking at this linear order, then we want to pick some representative. And because the rationals are dense, we can pick a representative that is between the representatives of previous blocks discovered to the left and to the right of this new block. And so our representatives keep this order preserving this. They also came up with the notion, if we add strictly to support strictly otherwise monotonic increasing, then the definition here is just F restricted to S is strictly increasing. So we can define some class of sets using this notion. So we define the class sum 0 jumper Q to be set of all. Sum 0 jumper Q is a set of all A such that A is the range of a 0 jump support increasing the Limitwise monotonic function of Q. And S sum 0 jumper of Q is the set of all A such that A is the range of a 0 jump support strictly increasing the Limitwise monotonic function of Q. So we see classes. And then Ketch and Turetsky were able to come up with some characterizations using these classes. So notably, A is a member of S sum 0 jumper Q if and only if A is a computable increasing AD representation. They were also able to show that every delta 03 M degree is a computable increasing AD representation. So not every delta 03 set, but every delta 03 M degree does. Also, they were able to show, similarly to how Harris showed, that if a function A is the range of a Limitwise monotonic function, or 0 jump computable Limitwise monotonic function, then it has a strong AD representation. If A is a member of S sum 0 jump Q, then A has a computable strong AD representation. However, this is only in one direction. And Turetsky was able to give a counterexample to show that there is a set A, which is an S sum 0 jumper Q, but A does not have a strong AD representation. That sort of ends the first part of the talk. And so we'll get some observations about the existing work. The first is that both the characterizations, so of AD representation and increasing AD representation, these both involve relativizing something to 0 jump. And in fact, here I'm saying that you can show that these are relativizations of characterizations of computable sets, of sets with computable AD representations with a computable successor relation. And so another observation is that in both these proofs, the construction of the AD representation constructed all the blocks separately. So it did not take advantage of the fact that when built in a linear order, we can merge blocks if we want and say, all right, we'll make everything successively keep this block. And so it built up the blocks individually and only broke them apart. So essentially what this meant was that 0 jump could compute the block relation for those AD representations that were constructed. So looking at the first observation, it makes sense to come up with the following definition. An AD-S representation of a set A is a computable AD representation L, where the successor relation is also computable. Similarly, a strong AD-S representation of a set A is a computable strong AD representation of computable successor relation. Since all the existing characterizations could be seen as relativizations of characterizations of AD-S representations, the hope is that we can come up with a characterization of strongly AD-S representable sets and turn this into a characterization of the AD representable sets. All right. And we do, so back to the second point, this is in fact quite important that 0 jump can compute the block relation, and we're able to use this notion to come up with a characterization of S sum of Q in terms of strong eta representations. So a set A is a member of S sum 0 jump of Q if and only if there is a computable strong eta representation of a 0 jump computable block relation. So this is kind of important for how we go about trying to come up with a characterization. But if we combine it with Turecki's result, this means that any characterization of a strongly eta S-representable sets, when we construct the eta representation, we must allow for blocks to be able to merge. It's no good to construct them individually. So this motivated the following definition. Look at this notion of connected approximations. So definition here. So a connected approximation to a set A is a sequence of finite functions, again, with associated sequences of finite sets A and M that satisfy the following conditions. So the first condition, we want that the range of Cn is a subset of the domain of Cn plus 1. So they each are mapping into each other. And then using these Cn's, the An's are defined as follows. So An0 is the domain of Cn. Then to get the next An in the sequence, so An plus 1, we apply Cn plus m to A and m, and we get the next set. So we basically take An0 and keep applying Cn, Cn plus 1, Cn plus 2, and so on. And the sequence of sets, we want it to have a limit. A and omega should always exist. And then to represent a connected approximation of A, and that A is just the union of all of these A and omegas. So some special types of connected approximations as follows. So we call a connected approximation monotonic if Cn of x is always greater than or equal to x. And we call it order preserving if Cn preserves less than or equal to. So the intuition about what these connected approximations are doing is a little bit different. So here the idea is that the elements of the domain of Cn correspond to some blocks of an eta representation that we can work out at size n. All right, and so the Cn tells us sort of what happens to the blocks. So Cn of x should be the new size of the block at stage n plus 1, because that will be a member of the domain of Cn plus 1. And then Cn plus 1 may have added some new blocks. And the important part is that if we have two blocks, Cn of x and Cn of y, and they map to the same thing, then it should be represented that those corresponding blocks of our eta representation merged at stage n plus 1. So using connected approximations, they would come up with the following characterizations. So for a set A, so A has a computable connected approximation if and only if A is sigma 0, 2. So if we don't put any conditions on it, it doesn't do much more than Limitwise monotonic stuff. All right, so A has a computable monotonic connected approximation if and only if A is the range of a computable Limitwise monotonic function. So then, and then A is a computable monotonic order preserving connected approximation if and only if A is a member of sum Q, and A is a monotonic order preserving connected approximation where each Cn is injective if and only if A is a member of S sum Q. So if we relativize the middle two results to 0 jump, you can see that this is a new characterization of the eta representable sets and the increasingly eta representable sets. And it was able to get a characterization of the strongly eta S representable sets. So A has a computable strong eta S representation if and only if it is monotonic, order preserving, as a connected approximation, which is monotonic, order preserving, and they satisfy this following condition psi. So what psi here says is that blocks can merge. All right, but when blocks merge, the new merged block must now have quite a large size because it must include further sizes of all the blocks which are merged into it, plus all the points in between them. So this sort of n here is corresponding to the fact that we're assuming at stage n we put n many points between them. And so the later the stage, the more points we've put in between blocks, assuming they were separate. And so the later the stage we see they merge, the larger the resulting block must be. All right. However, unlike other results, this doesn't relativize. So if we relativize it, we get one direction. So if A has a computable strong eta representation, then A has a zero jump computable monotonic order preserving connected approximation, where each Cn satisfies psi. Unfortunately, this is only in one direction. So it's an open question. Is there a set with a zero jump computable strong eta S representation, but no computable strong eta representation? All right, so that was the sort of closest I got to characterizing the sets. But if we look at degrees, we can do a bit better. So there's a nice density result I got for strong eta representations in S-SOM. So suppose that G is a computable function which is increasing. There we go. And if a set A has a strong eta S representation and satisfies the condition that A intersect with D, G of n is greater or equal to n, then A is a member of S-SOM of Q. So if it dense enough sets, maybe something like A join omega, we're going to have the notion that eta S representations correspond to being a member of S-SOM of Q. So we can relativize it and get a characterization for dense enough sets as follows. So for a set A, suppose that there is a zero jump computable increasing function G such that A intersect G of n is greater than or equal to n. Then the following are equivalent. A has a computable strong eta representation. A is a member of S-SOM zero jump of Q. And A has a zero jump computable strong eta S representation. And so, like what Lerman did and Characterization did by taking A and joining it with omega to get the degree characterization, we could also do the same thing. So we have the following lemma. If A is a set with a strong eta S representation, then A joining omega also has a strong eta S representation. So this relativizes, and then we can put it together with a density result, and we can get our degree characterization below. So the following sets all coincide. The m degrees of sets with a computable strong eta representation, the m degrees of sets in S-SOM zero jump of Q, and the m degrees of sets of zero jump computable strong eta S representations. All right, so that's the end of the talk. Thank you very much.
Thank you. Thanks, Josiah. So are there questions? Questions? People should just feel free to jump in if you have any.
So I have a question. So, which I suppose the answer is going to be no, but have you thought about or stumbled across any connections between these sort of stronger, higher level notions and, computable model theory? I mean, limit-wise monotonic functions turned up in various ways in constructing examples in computable model theory. And I'm wondering if these notions might also have some analogous uses.
Yeah, I haven't really looked into it that much. Yeah, I know that it's some more, Cash and Turetsky explored a little bit some other results about support increasing the multi functions, especially when they put, not just on Q, but on different linear orders. But for connected approximations, I haven't looked any further.
No.
It's actually a good question. Sorry, yeah, it's actually a good question because these Limitwise monotonic functions, they were originally defined by Josiah, right, in the context of torsion groups, right? So it might be, somebody, not necessarily Josiah, but somebody may want to look at the connection, between these notions and torsion-free groups, torsion-free abelian group, torsion abelian group, right? Abelian P groups, right, is really the right topic. This is what Josiah was studying. Because that's where it came from. So I assume that what Richard is really looking for is sort of a connection back to that.
Yeah.
Which is sort of this, but there may be other applications too that I'm not aware of. I only know 2 applications in computable algebra, groups and linear orders. But there may be other areas.
Yeah, there are other things, computable model theory and things with like alpha categorical structures and things.
Right. I was thinking of applications along those lines, which are a little farther, seem a little farther removed than the initial uses. I don't know. I don't know how you find these. That's why I didn't expect it to be a positive answer at the moment, but that's
good question.
Are there other questions? Okay, well, if not, let's thank Josiah again.